So today we're going to look at the last part of the haloalkanes topic, and we're going to look at CFCs and its effects on the ozone layer and how it breaks down the ozone layer. I'm going to show you the mechanism for this breakdown of the ozone layer, which is a radical substitution mechanism. So before we talk about the depletion of the ozone layer by CFCs, we're going to look at what the ozone layer is. The ozone layer exists in the upper atmosphere. The atmosphere is divided into different layers. So, for example, the troposphere is closest to the ground level, and the ozone layer exists in the stratosphere, which is in the upper atmosphere. The ozone layer is really important to us as it absorbs a lot of harmful UV radiation from the sun. UV light has a range of wavelengths, and we can categorize those different wavelengths into UVA, UVB, and UVC. And UVC is the higher frequency wavelengths, so they're more likely to be ionizing and damage DNA in cells. So life on Earth would be very different if the ozone layer wasn't present to absorb most of the UVC and prevent it reaching ground level. UVB within the UV range of the electromagnetic spectrum is also harmful, but we need UVB to make vitamin D in our skin, and vitamin D is important for bone health. As well, it's been shown to reduce respiratory infections, so some people think that's why we have fewer flu cases in the summer. Despite the name ozone layer, there's not a lot of ozone in the ozone layer, and in fact ozone can exist on ground level where it's considered as a pollutant. Ozone on ground level increases with air pollution, and the chemicals in air pollution interact with oxygen and the action of UV to produce ozone. And ozone on ground level can cause problems for people with respiratory health problems, things like asthma and chronic lung disease. So next I'm going to talk about how ozone is formed in the stratosphere naturally. So oxygen in the upper atmosphere, in the stratosphere, can be broken down by UV light, and the UV light has enough energy to break the double bond in O2 molecules. O2 molecules break down in the presence of UV light to form oxygen atoms. The two paired electrons originally in the oxygen molecule are now unpaired. So this is now not paired with this one. So that's an unpaired electron, and this is now unpaired, and so are these unpaired. So we have two unpaired electrons. So we call this a diradical. So these two are diradicals. So when we used to write formally for radicals, we used to use a dot. And because these are diradicals with two unpaired electrons each, we can write the two dots, but often we just don't write the dots at all because this is effectively an atom. So when oxygen breaks down in the stratosphere to make these diradicals, the diradicals, like any radicals, are very reactive and unstable species. So they would tend to react with things they collide with. So in the atmosphere, there will be a lot of oxygen molecules around to collide with these radicals, and when they collide they form ozone. So this is the dot cross diagram for ozone, which you drew when we did shapes of molecules, and you can see there's a lone pair, a data equivalent bond and a double bond. So these are reversible processes, and we can add these two equations to give us an overall equation to show what's happening in the upper atmosphere, in the ozone layer. Without any pollution, the forward rate of reaction equals the reverse rate. So the rate at which ozone is produced is equal to the rate of its destruction. So a dynamic equilibrium is formed, and we call this a steady state. So what we're going to do next, we're going to look at what CFCs are and how it destroys the ozone layer, and you need to learn the mechanism for this process. So CFCs are chlorofluorocarbons. They are a group of organic compounds containing chlorine and fluorine. So CFCs were considered safe as they were inert, at ground level at least, where there's not as much UV light, and they were used in lots of different applications. So in the back of your fridge freezer, you will see some black pipes, and inside of those are gases, and they get compressed in a motor, which you can hear sometimes. And those gases within the tubing are allowed to expand within, especially the freezing compartments, they're allowed to expand within the fridge freezer. And as they expand, they absorb heat from the surroundings to cool your fridge freezer. So CFCs were used as refrigerant gases, but they are now being replaced by alternatives. In the past, CFCs were used as aerosol propellants. They were used to propel the contents in a canister, something like a deodorant or hairspray. One of the reasons why CFCs were used as aerosol propellants is that they were very inert and didn't interact with the contents of the canisters. So CFCs were also used as foaming agents to make foam plastics. So they bubbled CFC gases as the plastics were formed. So polystyrene foam cups used to be made with CFC gases. So expanded polystyrene foam, called styrofoam, were used to make insulating cups and food containers for takeout food. Since the 1980s, CFCs have been phased out for these applications because although they are inert at ground level, they are reactive in the upper atmosphere where there's UV light, and they form chlorine radicals and halogen radicals. So these radicals can damage the ozone layer. We're going to look at next how CFCs catalyze the breakdown of ozone via a radical substitution mechanism. So we need to be able to explain in the exam using a mechanism how CFCs catalyze the breakdown of ozone in the ozone layer. So CFCs, which are relatively inert at ground level, can in the upper atmosphere break apart into radicals. In the exam, you need to be able to write the mechanism to show how chlorine radicals break down ozone through a radical substitution mechanism. The first step, which is the initiation, would be your CFC breaking down homolytically to form radicals. And one of the radicals you should write is a chlorine radical, because the carbon-chlorine bond is weaker than the carbon-fluorine bond, so the bond enthalpy for carbon-chlorine will be lower than for carbon-fluorine. So the first propagation step is where ozone collides with the chlorine radical from the propagation to form oxygen. One way to remember the two propagation steps is that each of them will form O2. So once you remember that the chlorine radical collides with ozone to form O2, you can work out what this species here is by balancing that first step. And we have a COO radical which balances this first step. This radical is shown to collide with oxygen diradicals. So these oxygen radicals already exist in the upper atmosphere, as we shown in the steady state equation before. These oxygen diradicals collide with the radical from the first step. And hopefully we remember that one of the products in the second propagation step is oxygen, as both steps will produce oxygen molecules, O2 molecules. So finally, we can work out what this is in two different ways, either by balancing this final step or by remembering this is the same radical as the radical in the first step. The chlorine radical is regenerated to go into the first step. So this is a chain reaction. If we add these two steps together, we get this, where we can cancel out the spectators, which are the regenerated chlorine radicals, and also these radicals. What we have is this. What we get is the reverse reaction of this steady state. So effectively, the CFCs are catalyzing the reverse reaction. So the speed of the breakdown in the steady state will increase. So the concentration of ozone in the stratosphere starts to decline. So this is how CFCs catalyze the breakdown of ozone in the ozone layer. So to recap, the initiation step of this radical substitution mechanism would start with the CFC breaking down homolytically under UV light to give you a chlorine radical. I've shown here more than one possible initiation steps. There should be two propagation steps. And the first one is the breakdown of ozone by the chlorine radical you produce in the initiation. To help you work out the two propagation steps, if you remember that each of the steps will produce O2, that would help. So if I know that ozone collides with the chlorine radical from the initiation step to give us O2, then what's missing would be the ClO radical, and I can work that out by balancing this first step. We can work out this second propagation step by remembering the radical from the first step will produce oxygen and regenerate the radical in the first step. So we can work out this from balancing the second step. There is one more video for this topic of haloalkanes, and that is how ozone can be broken down by nitrogen oxides in a similar mechanism to the radical substitution by CFCs. So I'm doing that as a separate video to help us revise this topic as well.